All right, recording is rolling. Welcome to Friday, November 3rd. Oh, did you guys turn your puzzles? You guys turn your puzzles? Right, so picking those up today. If you haven't turned them yet, just throw them in the grade tray before you walk out of class. I'll check this off and point in the grade book. I gave you guys your energy quiz a few days back, so let's have that due on Monday. Remember how this working too? On Monday, we're going to start the next section, which is momentum and impulse. I gave you the thumbnail notes on those, and those are also those blue banner posters over there on that wall. And so then do our same routine, 2 weeks, take on quiz the whole day. Okay. But then at the end of that, I'm going to give you guys a quiz on both energy, which we're just wrapping up today, and momentum, which we're going to start next week. That'll be an in-class quiz, closed notes, right? Because all the physics teachers are giving the same assessment. It's like a common assessment thing. So just look forward to that about 2-3 weeks from now.
So that's going to be this unit and the next unit?
Yeah.
Okay.
Energy momentum.
Okay.
Energy momentum.
And momentum's next.
That's it. Okay. Momentum's next. Yeah. All right. So I got a couple of demos for you guys. There's an FRQ on your desk, so we'll look at that in a few minutes. But all right, before we hit that, switch your screen over here. All right. So I think something I mentioned was this Pinewood Derby car they mentioned. Right. Do you guys know this YouTube channel, Mark Rober? Right. Okay. Yeah. So some of you guys familiar, right? I think he was a NASA engineer at one point. Now he has this YouTube channel. So one of his videos goes back a few years is gives you tips on how to construct these Pinewood debris cars. So let's see what this looks like. You get this box, right? Okay, there you go. They're racing, right? But you guys saw the racetrack, right? So put 2 or 3 cars at the top, and then they just go down, right? Right. So what's the tricks to winning this? He goes through some physics principles about how to design a better car, and also some like actual empirical science, right? Here's one of those tips right here, right? It's like, where do you load the weight on the car to help you out? Like, do you load it closer to the front or closer to the back? Well, if you load it closer to the back, notice he's got kind of a simplified cartoon version of the slope they're on, right? Because really it's like more like a gradual slope, but the principle is the same, right? This blue car is done picking up speed, right? So whatever speed it had is just done picking up speed, right? But this red car, you see it's still kind of elevated. So if you put the weight near the back, right, because it has more gravitational potential energy from the start, which means that by the time it gets down to this flat section, it's going to have more kinetic energy because conservation of energy, right? What I'm really looking for is, let's see, it's about, it's not giving me the timestamps down here. Looking for about, okay, 6 minutes. And he gives lots of tips, but there's what I'm looking for this demo. Okay. So, look at this. It's a conservation of energy equation. He sets it up with blocks. I like the blocks. I think that's a nice visual, right? So all these blue blocks are the initial gravitational potential energy, all your mgh. Oh, look at that. Weight times height. There's your mgh, right? And then again, if you slide the weights kind of towards the back of the car, you give even more mgh, a little bit more, right? There was like an optimal place to put it. It's not the exact back, but it's kind of like near the back. Right. And then that could turn into what kind of energy? Now, how I've been having you guys set these equations is more like what I would think AP would do. Is more like an open system where you would subtract this friction. So it's a minus the 2 red blocks equals, and then you have whatever left over, right? He does this way. It's just a different perspective. It's like, well, you start with this, and then it equals, and then it goes to like maybe these 3 different places, right? So kinetic energy, there's your energy motion, and then there's some difference that goes into maybe like frictional losses, like these red blocks here, right? Right. But this kinetic energy, he's got 2 kinds of kinetic. He's got this green translational kinetic. There's your 1/2 mv squared, right? And then he's using these yellow blocks to represent rotational kinetic. Now, those are just the wheels, right? The wheels are rotating. Now, I've kind of touched on this, but we haven't got super depth, but we will in December. In December, this is going to come back. We're going to say, hey, what does it look like to have like a ball rolling down an incline, right? And in this case, we got like 4 of them. We got like 4 wheels rolling, right? So there's some energy that goes to make those wheels rotate. And one of the biggest tips to winning these Pinewood Derby races, or if you ever find that opportunity, is to actually not make the car rest on all 4 wheels. So somewhere like later towards the end, he says, actually bend up one of the axles so the car is only riding on 3 wheels. What that does is it takes like one of these yellow blocks, which represents energy to make the wheel rotate, and it no longer has to rotate, right? It's just sitting there, right? So he's going to flip it and turn it into like one of these green blocks, right? Which represents translational kinetic energy, which has to do with like the car, like linear speed motion. So those cars are going to win the race, right? Because if only 3 wheels are spinning, the one wheel it's not rotating, well, that initial energy could turn into just making it go. So you flip one of these yellow blocks to a green block, right? It's going to win the race. You guys get that, right? So it's a whole long video. I'm going to show you guys the whole thing. That's some of the main highlights of that and the conservation of energy connection. Right, the other demo I want to show you guys, now this is something really weird, something called hydraulic jump. Let me start with the videos that aren't super good, but kind of get the idea across, right? I was like, okay, can water flow uphill, right? Well, you tend to not see like balls rolling uphill or water flowing uphill. That would look weird, right? But every once in a while, you can get conditions that are right for this happening. And this one is like a storm drain. You see the water flowing uphill. What the heck is going on there? Right? Here's another one. When I was in college, I took two classes in water. One was hydrodynamics, one was hydraulics. Those were some of the hardest classes I ever took. Right? Some crazy properties. But the basic foundation was like conservation of energy, Vernal principles, just like conservation of energy, some things, right? But then you can go like deeper, deeper, deeper. Say, well, water has all these like, weird electrostatic properties, and you can make it more complicated. Right? And this is like, one of the weirdest phenomenon. Okay, now here's like the kind of clean video. This is like the laboratory version, right? There's all different, like, okay, you have to know like electrostatic properties of water, and then if there's like some channel that has like some width and some depth, then you water flowing through at some speed and put everything together. But you can, if you just right, like it what's called a hydraulic jump, where there's actually like a increased high level of water. You can see right there. Yes, it goes from a shallow end to a deep end, right? Which is not something that you that. So if I pause it right about there, right? Okay, so it looks like it's set pretty stable. All right, so if you calculate like the energy in this part, you do so kind of 1/2 mv squared, right? And then you calculate the energy here, 1/2 mv squared. Now it's a slower speed, right? But it's also deeper, so you also have got to add the mgh, right? Um, you say, well, where is there more energy, right? And there's more mechanical energy actually in the shallow part here because there's a lot that's lost to this hydraulic jump right here. There's a lot of turbulence here, right? And that energy, again, it doesn't disappear from the universe, but it might go like thermal energy. So if you put a thermometer here, put a thermometer here, but the water heats up a little bit in this section, right? There's a problem. Right? All right, so there you go. That's a fun one. All right, you guys ready for this FRQ? FRQ.